So today we are very pleased to have Andrew Rhodes from Toulouse School of Economics, who's going to talk to us about digital ecosystems and data regulation. Andrew, you have 40 minutes.
Okay, let me start again. So thanks a lot to the organizers and thanks everyone for coming along. So this is joint with Jidong Zhou from Yale SOM and Junjie Zhou from Tsinghua. So I'll try and be quite brief with my introduction. So nowadays, big tech companies increasingly operate as so-called digital ecosystems, which supply a wide variety of different products and services. A good example of such an ecosystem would be Google, which at any one point in time usually offers hundreds of different products, around 70 of which I believe are targeted at final consumers alone. Google, as you all know, is active in a variety of different markets, ranging from search to video, maps, payments, and now, of course, also AI. Now, we would argue that ecosystems like Google have at least two interesting and important features. So the first is that they collect a lot of data from their customers, but also because they're active in many different product areas, they can leverage data from one market to change the offering that they provide consumers in another market. The second thing, which we think is important, is that ecosystems often compete not just with each other, but also with smaller specialized players. So here we have a selection of Google products at the top, ecosystem competitors at the bottom, and for each of those products in the middle, we also have a different small specialized competitor. Now, just to flesh these last 2 points out a little bit more, notice that if we stick with the example of Google, Google is able to use, for example, spending data from Google Pay, location data from Google Maps, and also fashion trends from Google Shopping to offer better and more relevant search results in a way that a small specialized competitor like DuckDuckGo may not be able to. Notice also that Google can use information from search and also metadata from YouTube to train its AI chatbot Gemini, again in a way which even a very well-resourced incumbent like OpenAI arguably wouldn't be able to do. Okay, and so for this reason, some commentators have argued that Gemini will soon catch up with and even surpass ChatGPT. Now, this access that ecosystems have to data and their ability to leverage it across markets has raised some concerns amongst policymakers. So here's a quote from the Australian Competition Authority. They start off by saying, well, data in and of itself is a good thing, and use it, for example, to offer a better quality of service. However, smaller competitors who may not have access to the same volume or scope of data may be put at a competitive disadvantage. And so the concern is that these smaller firms, because of this disadvantage, may not compete so aggressively, may not innovate so much, and that ultimately this may lead to lower consumer welfare. Now, of course, there are concerns around ecosystems' use of data. There's also currently a lot of regulatory activity surrounding their collection and usage of data. So two policies which are going to be particularly relevant for what I'm going to talk about today are, first of all, GDPR, which places some restrictions on how much data firms can collect and what they do with it. And secondly, the DMA. So, of course, there are many parts of the DMA. The parts which are perhaps most relevant for our model surround the clauses which put restrictions on how data from different businesses or core services can be combined, as well as clauses which mandate data sharing, for example, for search engines, and which facilitate data portability. It's also worth bearing in mind that there's also a lot of firm-specific regulation. So in China, Ant Group terminated a data sharing agreement with its former parent company head Alibaba, and in India last year, WhatsApp was temporarily banned from sharing data with other Meta entities. Okay, so there are concerns around ecosystems' use of data, but there's also some regulation which is trying to push back a little bit against that usage. So what do we do in this paper? Well, we really have two goals. So the first goal is to try and build a tractable model to look at competition between a multi-product digital ecosystem and specialized single product competitors. As you'll see in a moment, the framework is one in which the ecosystem is able to leverage data from one market to improve its products in other markets. In each of these markets, there's going to be competition in both price and innovation, and we're going to allow for rich heterogeneity across products in terms of how they generate and use data. Once we have that framework in place, we then want to use it to try and understand the impact of different data policies, including some of the ones that I mentioned on the previous slide. So we'll look at the effect of policies that restrict an ecosystem's ability to generate and use data. We'll also look at policies which mandate the ecosystem to share at least some of its data with small firms. And we'll also look at the incentives and welfare impact of data cooperative formation amongst small firms in the marketplace. I think in the interest of time, I'm going to skip over the literature, but I'll be very happy to come back and discuss that later on. Let me jump straight to the outline of the talk. So I'll start with the model. I'll spend some time giving a sketch of how we solve the model. Then the core of the paper is data regulation, which has some semblance to GDPR and DMA. And then depending on time, at the end, I'll discuss other policies that we look at in the paper. So let me start with the model. So the model is relatively simple, although there are a few different moving parts. So we're going to have a continuum of independent product markets, and we're going to normalize their measure to 1. In each market, there's also going to be a unit mass of consumers who are interested in buying this particular product or service. For what I'm going to talk about today, it's not really going to matter whether we have the same consumers or different consumers in each market, or whether there's some overlap in the consumers who are present in different markets. What's really important is the overlap in the firms. Okay, so what we're going to assume is that there's one multi-product ecosystem which operates in all of these product markets. And then in each market, it competes with a different specialized single product firm. Competition in each of these markets is going to take place both on price and quality investment or innovation. Okay, so in particular, the ecosystem and the small firms are simultaneously in each market going to choose price and investment. Now, when I say price, depending on the product market we have in mind, this might be an explicit price, but of course it could also be an implicit price like advertising. So we're going to use P to denote price, V to denote quality investment or innovation. And when you see the subscript EI, this denotes ecosystem play in market I. And when you see SI, this means the small or specialized firms play in market I. Now, we're going to assume that this investment in quality is costly. And to keep things tractable, we're going to assume that costs have this quadratic form here. Okay, so for example, if in market I, the ecosystem invests an amount VEI, it's going to incur a quadratic cost given by this term here. Okay, and you'll notice that both here and for the equivalent cost for the small firm, we have these eta terms here. Okay, so we're not going to place any a priori restrictions on how these etas vary either across markets or across firms. So in particular, we're going to allow for the possibility that in some markets, the ecosystem is more efficient and innovating, i.e. it has a higher eta, whereas in other markets, it's the specialized firms who are more efficient, i.e. have a higher eta in investing. We're also going to normalize the production cost to 0. Formally, this is just a normalization, but we also think it makes a lot of sense given that we're thinking about digital products where the main cost is arguably fixed costs, say, of improving products. Now, in each market, the firms are going to simultaneously choose their prices and investments. Consumers are going to see these, and then they're going to make a choice in each market. Now, in terms of consumer payoffs, these are going to be influenced by the ecosystem's collection of data. Okay, and so in particular, we're going to assume that the ecosystem generates a volume of data Q, which is defined in the following way here. Okay, so to understand what this says, ZI denotes how much, so the fraction of consumers to whom the ecosystem sells in market I, whereas alpha I tells us how effective market I is at generating data. So in each of these markets, every time the ecosystem sells, it's going to collect some information, it's going to aggregate that together, and that's going to lead to this variable Q. We're then going to take a benign view of data, although even with this benign view, we're going to see that the scope later on for regulation. So we're going to assume that the ecosystem, when it collects this data, it can use it to improve the quality of its products. And so in particular, we're going to assume that in any given market I, a consumer gets the following payoffs if she buys respectively from the ecosystem or the small firm. Okay, so if she buys from the ecosystem, the payoff is going to equal the ecosystem's investment V minus the price P that it charges, either implicit or explicit price. And then there's going to be this data-enabled boost term here. Okay, so alpha I is going to tell us how effective market I is at generating data, and beta I is going to tell us how effective market I is at using data to improve the product. Okay, and then finally, if you buy from the ecosystem, you're also going to have this match term here, this epsilon term, which just reflects product differentiation. So some people are more or less keen on the ecosystem's product than others. Instead, if in the same market I, a consumer buys from the small firm, her payoff is going to look similar. So she's going to benefit from the investment V that the small firm did. She's going to have to pay the price P, and she's going to get a taste shock. However, in our baseline analysis, and this is something that we'll discuss and relax later on, there's no data-enabled boost term here. Okay, so the idea we want to capture is that all of these small firms, because they're small and specialized, they don't have access to the same volume and scope of data as the ecosystem does. So just to be clear again, these alphas and betas are both going to be at least weakly positive, but they're allowed to differ across product markets. So some product markets may be better at generating data, others may be better at using data. Now, for simplicity, we're going to assume that each of these product markets is fully covered. So in each market, a consumer is going to buy either from the ecosystem or from the relevant specialized small firm. Okay, and so obviously, what matters is not the absolute values of these taste shocks, but rather the difference. So we're going to assume that the difference in taste shocks is distributed according to a CDF, capital F, and we're going to suppose that it has a log concave PDF little fi, which is symmetric around 0, and Li is going to denote the support of that distribution. Okay, so that's the model. So let me just quickly recap to make sure everyone is on the same page. So we have this unit mass of product markets. In each market, we have a unit mass of consumers. There's one ecosystem which supplies everything, and then it competes in each market with a different specialized single product firm. Competition takes place in both price and quality investment, so P and V. Investment is costly, and the more you do, it's increasingly costly. And these eta terms tell us for a particular player in a particular market how efficient that player is at doing innovation. So the higher the eta, the lower both the absolute and marginal cost of investing. The ecosystem collects data when it sells in these different markets. It collects it together to form this, what you can think of as a data set or a volume of data, Q. It can then use that data to improve products. Alpha I tells us how good a product is at generating data. Beta I tells us how effective a product is at using data. And then finally, markets are fully covered, and differences in taste shocks are distributed according to this distribution F. Okay, so if there are no questions, let me move to how we solve the model. Okay, so let's start by thinking about the consumer side here. Okay, so let's fix a particular market, I, and let's ask in that market, what should a consumer do? Okay, now consumers are going to observe all of these prices and investments. So they should then form a rational expectation about Q, the volume of data that the ecosystem is going to collect. Okay, that then allows consumers to pin down their utility or their surplus from buying from the ecosystem. Okay, and then very simply in market I, a consumer will buy from the ecosystem if and only if the following inequality holds. Okay, so in particular, if their relative preference in terms of taste shocks for the small firm is low relative to the difference in deterministic utilities or surpluses that they get respectively from the ecosystem and the small firm. Okay, so in other words, in market I, consumers are going to buy from the ecosystem if their taste shock is less than this object, which we're going to call delta I. Okay, and so delta I, this is going to crop up again in the following slides. Delta I is going to tell us in market I the identity of the marginal consumer. Okay, and so given that this difference in taste shocks has a distribution F, we can write out the ecosystem's demand in market I in the following way. Now, notice that we should check that these demands are well defined and that they're unique. So that's true under a relatively mild condition, which we have in the paper, and which is going to be imposed by, which is going to be implied by later conditions that we're going to impose. Okay, so this consumer choice game has a unique, well-defined equilibrium. Now, notice, and this is going to be important when we come to the firm side of the problem, even though these markets are formally independent, because of these data spillovers, they become interlinked. Okay, and so in particular, there's going to be demand complementarity. Okay, what do I mean by that? Well, imagine that in a subset of markets, the ecosystem either does more investment V or it charges lower prices P. Okay, suppose it does that in a positive measure of markets. Well, you can see from here that the marginal consumers in those markets are going to shift. And so, of course, the ecosystem is going to sell more in those markets. Assuming that at least some of those markets have a positive alpha I, the ecosystem is then going to generate more data. Okay, and so in all other markets where beta I is positive, the ecosystem is now going to offer higher utility. And so it's also going to sell to more consumers in those markets. Okay, and you're going to get a chain reaction, which in the end is going to mean that raising investment or lowering price in some markets is going to lead the ecosystem to sell more in other markets as well. Okay, so this is the consumer side of the problem. Now let's turn to the firms' problems. So what we're going to do is we're going to look for an interior equilibrium where Zi is strictly between 0 and 1. So remember, Zi is ecosystem sales in a particular market. Okay, so we're going to look for an interior equilibrium where in each market, the ecosystem sells to some, but not all of the consumers. Okay, so let's start off with the single product firms and their problem. Now notice that because we have a continuum of firms here, each individual single product firm has a negligible effect on capital Q, on the amount of data that the ecosystem collects. Okay, and so when a small firm chooses what price or investment it wants to set, it's going to just take this Q as fixed. Okay, and so in a particular market I, the single product firm wants to maximize its price multiplied by its demand minus the fixed investment cost. Now, if we take first order conditions, we get the following. Okay, so we can think about this in two ways. First of all, we can think about optimizing individually with respect to P and V. Okay, and so imagine that the ecosystem wants to sell to a few more consumers. First of all, it could cut its price. What is the cost to the ecosystem? Well, it's the lost revenue on all of the people it's selling to. Or if it wants to sell to more consumers, it could slightly raise its investment. And given that we have this quadratic investment cost, this is going to be the marginal cost to the ecosystem of doing a little bit more investment. What is the marginal benefit to the ecosystem of cutting price or doing a bit more investment? Well, it's going to shift that delta. It's going to shift the marginal consumer. Okay, so it's going to sell to more consumers. That's given by this FI term. And when you sell to an extra consumer, the benefit is that you're going to get the price from selling to those consumers. So if we put these first order conditions together and solve them, what we find is the following. So first of all, for single product firms or specialized firms, the price just takes the standard format, which just depends on the elasticity of demand, right, which is given by this inverse hazard rate. And we find that small firms' investments are proportional to how much they expect to sell, with the factor of proportionality being the eta, so how efficient they are at investing. So another way to understand why we get this particular expression here is to notice that we could alternatively think about the small firms as choosing the delta I. So we could think about small firms as choosing exactly how many consumers they want to sell to, and then they need to choose the price and investment in order to hit that marginal consumer in the most effective way possible. And intuitively, if the small firm has decided it wants to sell to more consumers, well, the marginal cost of achieving the desired demand through cutting price is relatively high, and so the small firm is going to do relatively more investment in order to hit that marginal consumer. Okay, so this summarizes the price and investment that a single product firm is going to charge in a particular market. So now let's think about the ecosystems problem. Okay, so this is more complicated for two reasons. So first of all, the ecosystem is choosing a price and investment in a whole continuum of markets. And secondly, because of that, it also has to take into account that when it changes those price investments, it's now going to move Q. It's going to affect the amount of data that it collects, and therefore it's going to affect its product offering in other markets. Okay, so the way we're going to tackle this is to characterize the equilibrium. We're going to use the Lagrangian approach, and we're going to treat that Q equation, that data generating equation that I showed you at the beginning, as a constraint with a Lagrange multiplier lambda, which captures the shadow value of an additional unit of data. Okay, and so if we set up the problem like this, so again, ecosystems profit in a particular market, it's price multiplied by demand, minus its investment cost, integrated over all of these markets. When we take first order conditions, first of all, in any given market I, with respect to price and investment, we get the following. Okay, so the marginal cost of a price cut or an investment increase are the same as they were for the small firms, but now the marginal benefit of those two things is a little bit different for the ecosystem. So notice that now if the ecosystem sells to more consumers in market I, it's again going to get the price on them, but now it's going to generate more data. Okay, and how much data it's going to generate depends on the alpha I, and the value of that extra data is given by the Lagrange multiplier lambda. Now, if we solve these first order conditions, we're going to find the following. So first of all, the pricing expression is now a little bit different. So the ecosystem's price in a particular market looks like the standard elasticity rule. However, there's now a discount here. Okay, and so other things being equal, the ecosystem is going to subsidize data collection, and other things being equal, the subsidy is going to be larger in markets that are better at generating data, so where alpha I is larger, and the subsidy is also going to be larger when the value of data lambda is larger. However, if you work through these first order conditions, you're going to see that investment still takes the same form as it did before, so it's proportional to how much the ecosystem is planning to sell in market I, with the factor of proportionality being how good it is at investing. And a way to think about this is that, again, the ecosystem can be viewed as in each market, choosing a particular cutoff consumer, and then it's trying to find what is the cheapest way of selling to that marginal consumer. Now, of course, we still have to pin down the lambda. So if we take another first order condition and we substitute in from here, we'll find that the Lagrange multiplier takes this form here. Okay, what is the intuition behind this? Well, notice that if I give the ecosystem an extra unit of data, the first thing it could do is it could just raise price in each market by the relevant beta, right? Because if there's more data, we've made the ecosystem's product better, and so it can raise price and still sell to the same number of consumers. What is the value to the ecosystem of being able to raise prices in this way? Well, in market J, the value is precisely the extra data, the extra price it's going to get on all of the consumers that it's selling to, the F. Okay, so if we integrate that over all of the markets, this gives us the ecosystem's value of data. Okay, and so what we've done here is we've solved for ecosystem prices and investments, small firm prices and investments in each market as a function of these delta I, as a function of these cutoff consumers. Okay, that's fine, but of course, remember that these cutoffs themselves depend on all of the prices and investments that are being set in all of the markets. Okay, and so what we need to do now is we need to pin down these delta I. Now, if you remember at the beginning, we defined this delta I as just the difference in the deterministic payoffs in a particular market when buying from the ecosystem relative to the small firm. Now, if we plug in the expressions that we just derived for investments and prices in each market and solve this implicit equation, or this equation, we can get an implicit expression for the marginal consumer in a particular market as a function of lambda, value of data, and Q, the volume of data. Okay, in turn, this allows us to do the following. So if you remember, we have this definition of Q, the amount of data, and we derive this condition lambda on the value of data. So we can now boil everything down to a system of two equations in two unknowns, namely lambda and Q. Okay, and so the proof strategy here is going to be the following. If we can pin down lambda and Q, we can then, through this equation here, we can pin down all of these critical consumers, And then using the expressions that I derived on the previous slides, we can then pin down the prices and investments in all of the markets. Okay, so that's the approach that we're going to take. So first of all, existence of a solution here just follows from Brouwer's fixed point theorem. Now, we still need to check that the solution is interior. And ideally, we would have a unique solution because we're going to want to do some comparative statics with respect to policy variables in a moment. So we can use a Garel-Nikado theorem to find a condition under which the lambda Q which solves this is unique. Okay, and so obviously if we have a unique lambda Q, we have a unique cutoff in each market, and therefore we also have unique prices and investments in each market. So that's the first thing. Secondly, of course, we've taken first order conditions. We need to check that they're actually sufficient to characterize the equilibrium. So this is the more challenging part of the existence proof, given that the ecosystem is active in a continuum of markets. And so we need to think about arbitrary deviations across all of those markets. So we apply a different approach from the Lagrangian method. So we work in quantity space, and we again derive conditions that ensure that the first order conditions are sufficient to characterize the optimum. Now, I have the conditions in the backup slides, but in both cases here, what we need is basically what you would expect. Okay, so what we require is that in each market, there's enough product differentiation relative to these data spillovers, so the alpha and the beta, and relative to the investment parameters, i.e. the etas. Okay, so I think we're very familiar with the idea that in these kinds of markets, if data spillovers are too large, we could, for example, get multiple equilibria, because if we think that the ecosystem is suddenly going to be selling more in all of these markets, well, that will enable it to collect more data, to offer better products, and so that might justify consumers' initial expectation that the ecosystem is going to sell more. So our conditions are essentially ruling out that kind of scenario. So they're ensuring that this demand complementarity is not too strong. Let me just mention, of course, that while I think that intuition is very familiar, here we have an additional channel through these investment parameters. So again, if these etas are too large, then we could get multiple equilibria, because if we think the ecosystem is going to sell more in some markets, then we expect it to invest a lot more. We expect the small firms to invest much less. Okay, and so that might then mean that the ecosystem's products are much better, which again validates consumers' initial expectation that the ecosystem is going to sell more. So in a nutshell, we have conditions which rule out these kinds of things happening. Now, before I go to the regulation part, let me just mention one other thing, which is that the model becomes much more tractable in certain special cases. So when spillovers are small or when products are symmetric. And it turns out that when in each market, the FI, so the distributions are uniform, then we can completely solve the model in closed form solution. Okay, so I think I have about 10 or 11 minutes left. So let me turn to data regulation. Okay, so we have a lot more detail in the paper, but given the time constraint, I'm just going to give you a high-level overview of what we do, and then I'm going to give you a couple of examples. So notice that given the baseline model that I've presented to you, there are two natural types of regulation that one might think about. The first would be to reduce the alpha I in a positive measure of markets, which means that we make it harder in those markets for the ecosystem to generate data. An alternative policy would be to reduce the beta I in a positive measure of markets, which means that in those markets, we make it harder for the ecosystem to use data to improve its products. Now, it's going to turn out that both of these policies have qualitatively the same effect. Okay, so we're just going to deal with them together. Now, given what I said in the introduction, you might ask the question, first of all, so does this type of regulation benefit the small firms? And according to the model, the answer is unambiguously yes. Why? Well, intuitively, this type of regulation, because it's making it harder for the ecosystem to generate data and then use it to improve products, the first impact of this regulation is to weaken the ecosystem's product offering, at least weakly, in all of these markets. Okay, this is going to, first of all, shift demand towards the small firms. They're going to be able to charge more because their demand becomes less elastic. they're going to invest more. And even once we take into account all of these changes in prices and investments, the small firms are going to sell more at a higher price, and so they're going to earn more. Now, importantly, although perhaps this is already obvious, there's also going to be a propagation throughout the whole system here. Okay, so in particular, if we think about doing this regulation on just a subset of the markets, small firms in other markets which are not directly affected by the regulation are also going to benefit. Okay, why? Well, one can show that this regulation is going to lead in equilibrium the ecosystem to generate less data and so offer worse products even in markets which were not directly affected by the regulation. Okay, so this kind of regulation unambiguously benefits the small firms. What about the ecosystem? Well, so does regulation always harm the ecosystem? According to the model, the answer is no, not necessarily. Now, before I explain the intuition behind this, let me just qualify this result a little bit. So this result is just starting from an arbitrary collection of alphas and betas. Okay, so we've just taken those as fixed. Now, if we imagine that the ecosystem could perhaps at some cost choose those alpha and beta, okay, suppose it were able to commit to how it was going to use data, then of course we wouldn't expect the ecosystem to be harmed by regulation. However, we would expect it to always be harmed by regulation. It would never benefit. However, the result that we have here would give you a steer on exactly how the ecosystem would want to choose the alpha and beta across the different markets. So why, starting from arbitrary alpha and beta, can the ecosystem sometimes benefit from regulation? Well, on the one hand, as we've already seen, the regulation is weakening its product offering. Okay, so it's going to sell less, which is bad, but it's also going to invest less. Okay, and so it can recoup some profit there. But more importantly, if you think back to what I mentioned when I was discussing the small firms, this regulation is going to reduce the amount of data that the ecosystem collects. And you can show it's also going to reduce lambda. It's also going to reduce the value of data to the ecosystem. Okay, so if you think back to when we derived the ecosystem's price, it had this standard looking term minus a subsidy. Okay, and so what you can show is that the regulation is going to reduce the ecosystem's incentive to subsidize data collection. It's going to compete less fiercely for data. And so it may end up charging a higher price. And one can show, and I'll have some examples in a moment, that this can be so strong that actually the ecosystem can benefit from softened competition due to the regulation. Finally, we might ask, so does the regulation benefit consumers? And again, unfortunately, the model says no, not necessarily. There's a trade-off. So on the one hand, because fewer consumers are buying the ecosystem's product, it's easy to see that this means that it's, at least in relative terms, its offering is becoming worse. Okay? So consumers are facing a relatively worse product from the ecosystem than they did before in all of these markets. And moreover, we saw that the small firms are going to charge more. Okay, so this is all bad for consumers. The good countervailing effect, though, is that, as we also saw, the regulation is going to encourage small firms to innovate more. Okay, and so we have a more precise condition in the paper, but regulation here is going to benefit consumers if and only if small firms are relatively efficient at investing, and therefore if and only if the regulation is going to lead to a relatively strong innovation response from the small firms. Let me also just mention, before I come to some examples in passing, that while this is not the focus of the paper, at least when products are symmetric, we know that there's an interesting link between regulating the beta I and breaking up an ecosystem. Okay, so in particular, what we show in the paper is that if we were here to break up the ecosystem into two equal parts, that would be equivalent to just halving all of the beta terms, at least in the symmetric case. Okay, and so you can already see from this result here that if you want to use the model to think about what would be the impact on breaking up the ecosystem, it really depends on how efficient small firms are at innovating. That's going to be good for consumers if and only if the small firms are relatively efficient at innovating. Okay, so we have more results in the paper, but I thought it might be useful just to quickly go through a couple of examples. So let's start with an example where small firms are relatively efficient at innovating. So what this means is that the regulation is going to lead to a relatively strong innovation response from the small firms. Okay, and so what we're then doing here is we're plotting beta against here ecosystem profit and here consumer surplus. Okay, and so remember regulation therefore would mean a decrease in beta. This is just for symmetric products, hoteling example. So what you can see here is that when the small firms are relatively efficient at innovating, beta regulation is going to reduce the ecosystem's profit, as one might expect. The impact on consumer surplus is a bit more subtle. It depends on where we start. If we start with a relatively low beta, you can see that the regulation is going to benefit consumers through this additional investment by the small firms. But you can see that if beta starts very high, then the regulation could actually harm consumers. Why? Well, if the beta is very high, this means that the ecosystem is offering very good products to begin with. And so the regulation is going to dramatically reduce the quality of the ecosystem's products. That's going to, at least initially, outweigh any added innovation from the small firms, and that's going to harm consumers. Continuing with that theme, if we look at an opposite case where the small firms are actually much less efficient at innovating, then in that case, they're not going to respond very much to the regulation by innovating more. So consumer surplus actually monotonically decreases as we have tougher regulation. And actually, because of the softened competition for data, you can see that ecosystem profit is actually now increasing as the regulation becomes tougher. Okay, I think I have 3 minutes or so left. So let me just very quickly mention a couple of other policies that we look at in the paper, both of which I think are quite natural. So first of all, one might wonder, so, we've looked at these particular policies, but what happens if instead the ecosystem either chooses to or is mandated to share data with the small firms? Okay, so in that case, if we think about a particular, again, market I, the payoff from buying from the ecosystem is going to look exactly the same as it did before. But now the payoff, if you buy from the small firm, is going to be different. So we're going to capture this idea of data sharing from the ecosystem to the small firms through this parameter gamma I. So now alpha I tells you data generation, beta I is data usage by the ecosystem, and gamma I is data usage by the small firms. So now the small firms can also use data from the ecosystem to offer better products. Now, as I think is probably quite intuitive, for most variables, it's not going to make a difference whether you regulate by reducing a product's beta I or if you regulate by increasing its gamma I. Okay, and so data sharing, so raising gamma I, or restricting data usage, reducing beta I, is going to have the same effect on sales, prices, profits, and investments. Okay, and the intuition is simply that given we have a covered market, if you think about a consumer's choice between these two payoffs, what matters is the difference between beta I and gamma I. So anything that shifts that, that reduces that difference is going to have the same effect on consumer behavior and hence on all of the endogenous variables in the model. With one exception, which is that consumers are unambiguously better off, according to the model, with a data sharing policy than with a policy which restricts data usage by the ecosystem. And the intuition, again, I think is quite clear. Notice that if we were to restrict data usage by the ecosystem, so we reduce these beta I, one of the effects is that we're damaging the ecosystem's product, okay, which fixing everything else is, of course, bad for consumers. Whereas data sharing, again, fixing everything else, one effect of that is to improve payoff that you get from the small firm. So data sharing is kind of like raising all boats here, and therefore is a superior policy for consumers. The other thing that we do is we look at incentives of small firms to club together and form a data cooperative. So the small firms are now going to share data with each other, but they're still going to choose their prices and investments independently. Okay, and so now again, focusing on a given market I, a consumer's payoff of buying from the ecosystem is still given by the same expression that we had before, except now we're going to have a QE, just to make clear that this is data that is generated by the ecosystem, and beta EI is therefore usage by the ecosystem. And now if you buy from a small firm, well, the small firms also generate some data, which we're going to denote QS, and they're going to be able to improve their products according to this coefficient beta SI. Now, because the small firms still price and invest independently, they're still going to take these aggregate amounts of data as fixed. So we can solve the model in exactly the same way as we did before. We can write out first order conditions. We get exactly the same expressions we did before, with one small difference, which is that the ecosystem's price, although it looks the same as before, the Lagrange multiplier is now slightly different. We're going to have this additional term here. Okay, and so in this modified model, the value of data, other things being equal, is higher for the ecosystem. Why? Well, if you think about it, if the ecosystem now generates more data, that improves its product. Okay, so that's one reason why it could, for example, charge a higher price on a product. But now, if the ecosystem has more data, small firms have less data. Okay, and so that reduces their product offering, which gives the ecosystem a double reason why it can raise its price. Okay, now because this Lagrange multiplier is higher, because data is more valuable now for the ecosystem, it's going to, other things being equal, price more aggressively when there is a cooperative. Because of this effect, we're going to have stronger demand complementarity than we had in the baseline model, and so we're going to have slightly stronger conditions for existence of an equilibrium. So I think I'm maybe 1 minute over time. Is that true, Alex? Okay, so let me go very quickly. Don't look at the slides. I'll just say very quickly the main message from here is that one of the things we show in the paper is that small firms might not necessarily have an incentive to form a data cooperative. There's a trade-off. On the one hand, it enables them to offer better products, which of course is good. But as we've just seen here, it's going to induce the ecosystem to price more aggressively. And so, for example, in a symmetric setting, you get a very crisp result, which is that the cooperative is going to form if and only if the small firms are already dominant in the market, i.e. if and only if they sell to more than half of consumers in each market. Let me skip that and just wrap up. So the goal of the paper is to provide a tractable framework to study competition between a multi-product ecosystem and single product rivals. The model features rich product heterogeneity, data spillovers across markets, competition in both price and quality investment. We show that regulation benefits small firms. It's not necessarily bad for the ecosystem. It's not necessarily good for consumers. It's more likely to be good for consumers when small firms are more efficient at innovating. And finally, amongst other things, we show that small firms might not necessarily have an incentive to form a data cooperative because it induces the ecosystem to price more aggressively. Okay, so thanks for your attention and sorry for going a couple of minutes over.
Thank you, Andrew, for this very clear presentation. And now we have a discussion by JP Choi from Michigan State University.
Okay, so thanks for giving me an opportunity to discuss Andrew's paper on digital ecosystems. I consider this paper an exemplary applied theory work at its best, combining an elegant theoretical framework with practical relevance for data-related regulations. So the high quality of the paper is actually not surprising, given that the authors are among the best in their generation. So since the paper is already in good shape, I will not make any specific technical comments. I will just raise some general points. I'm sure the authors have already considered the points I will raise, but I will share them nonetheless to help open up the discussion for all participants. So my first comment concerns the assumption that all single product firms are major zero small players. So while this assumption makes the analysis highly tractable and allows for elegant equilibrium characterizations, an important next step would be to incorporate the strategic single product players into the analysis. I mean, at least single product firms, they can collect and they may be able to use the data for their own service improvement, even for not other small players. And my second comment concerns the evolution of ecosystems. All major ecosystem platforms initially established the dominance in their core product markets before expanding into adjacent markets to build broader ecosystems. So this raises several important questions, such as how these ecosystems grow and the role of the mergers, for instance, in this process. And perhaps the most interesting question would be how competition between the ecosystem unfolds. So whether they can strategically avoid the head-to-head competition, or whether product overlaps become inevitable. So additionally, the role of data in shaping these competitive dynamics would be very interesting for the extension. And my third comment is about the heterogeneity of data. Most studies on data consider only the aggregate quantity of data as a simplification. So however, different pieces of data can be either substitute or complement. So even in this paper, if I understand it correctly, the data generation process is additively separable, and the total aggregate quantity of data can be represented by a single number. But depending on the nature of data, collected from each market can be a complementary or a substitute. And the strategy of ecosystem can be very different, and the competitive nature might be also very different. And another aspect of the ecosystem we can consider is the privacy issues. The paper is somewhat silent on privacy concerns associated with data collection. So while any privacy costs associated with data collection could be incorporated by interpreting the consumer benefit in the model as a net benefit, there may be additional considerations for consumers. For instance, suppose a consumer requires two services, A and B, and both are provided by the same ecosystem. As a consumer, would the consumer prefer that a single ecosystem collect extensive information, or would the consumers opt to share less information but distribute it across multiple firms? In other words, do you prefer one firm having all information about yourself, but only one firm? Or would you like to share just a little bit of information, but with many, many firms? I don't know which, as a consumer, which would be a preferred outcome when we consider privacy issues. So finally, in this paper, consumers choose either the ecosystem or a single product firm for each individual market. And considering some exclusive tactics, such as bundling, that can be used by the ecosystem would be also interesting. And also in this context, it would be also important to analyze the ecosystem as a gatekeeper. As I mentioned earlier, many ecosystems are built around their core products, and many related services need to have access to them. So examples are like iOS or Apple ecosystem or Android ecosystem. And in these cases, the independent firms, in these cases, independent firms, maybe the ecosystem may be able to limit the access of the independent firms. And one example might be Apple's tracking transparency policy. So this is supposed to be used as a privacy protection policy, but may put competitors at a disadvantage. And these are some of the comments I have for this paper. And let us open the discussion to all of the participants. Thank you.